Hey guys, today we're going to talk about linear programming. So linear programming is used to find the maximum or minimum value of a problem that involves constraints. Well, that's great, but what's a constraint? A constraint, those are restrictions on the solution set. So it could just be something that's confining us to a certain region. So it'd kind of be if we met this function with this function meets this function, we kind of get pushed into this little area. And this area is called our feasible region. Feasible just because it's where it's possible, where we can possibly pick our solution set. So if we want to find our maximum or minimum, we're going to find these points, they're intersections that they like to call vertices because it's where the kind of endpoints meet. All right, so we have 5 little steps to help us when we're solving problems with linear programming. Step 1, define your variables. Step 2, you're going to write the system of inequalities. You're also going to find your function that they call an objective function that we're going to kind of use later, but that's probably going to be in those words too. So we want to identify that along with your system. You're going to graph the system of the inequalities and identify that feasible region, just basically where all the shading overlaps. After that, you're going to find the coordinates of the vertices, so those intersection points. Those are going to be our vertices of our feasible region. When you're done and you have your points, you're going to substitute those coordinates into the objective function to find your maximum or your minimum value. A few problems might ask you to do both. So let's start off. Oh my gosh. All right, you guys all appreciated that, right? So let's start off with some really simple example. Not over that yet. All right, I'm over it. So given the vertices of the feasible region, so they already found those points of intersection from our functions, and they found that one vertice was 4, 3, one was -2, -6, and the last one was -7, 2.5. They won't always be 3 functions, so there might be more than 3 vertices to your feasible region. There can't be less than 3 because the smallest polygon is 3-sided, but there can be 4 or 5. So we're going to use these coordinates, and here's the objective function, which got erased with my head, but you can see it's just f of xy equals 5x plus y, and if I want to find out which one is the maximum or minimum, I'm going to take this point here, start with the first one, and you're going to plug in the first part of your point is always x, and the second part is y, stays in alphabetical order, not that complicated, and I'm just going to plug it in. So I have 5x plus y now becomes 5 times 4 plus 3, and that is 20 plus 3, so I get 23 for my value. Well, I don't know if that's a maximum or minimum yet because I haven't compared it to the others. So I'm just going to move on to the second one. Same idea. -2 becomes your x value, and -6 becomes your y. So I have 5 times -2 plus a -6. Well, we don't really like that, so plus minus is just a minus. But we have 5 times -2 is -10, minus 6 gives me -16. Okay. Still don't really know because I haven't finished with this one. So I'm going to do the last point. -7 becomes your x, 2.5 becomes your y. 5 times -7 plus 2.5. Well, I get -35 plus 2.5 gives me -32.5. So now I substituted them all in, so I'm able to find my maximum. My maximum is just my biggest, so that's going to be 23. My minimum is the smallest, so the smallest value I got was -32.5, so that's my minimum value. And then it's really important to keep in mind that they might ask you the values that actually gave you this value. So it might be that your x represents the number of cars or y represents the number of buses. So remember, to get this maximum value, I really got that from the point 4, 3. So 4, 3 is the maximum point that gave me this maximum value. Same idea with the minimum. So the minimum value came from the actual points, -7 and 2.5, and of course we can't have -7 cars, but you get the idea. This could represent something in the real world. All right, let's take it up a notch and not get hit on the head. So, graph the following system of inequalities, name the coordinates of the vertices of the feasible region, and then find the maximum and minimum values of the objective function. And again, they go ahead and give us the objective function here, and they give us our nice little system of inequalities. So something right away you might realize is that your system of inequalities is actually made up of inequalities. Your objective function has an equal sign. So that can kind of help you. It's also written more as a function notation most times, where it's the function of xy. So if you want to try to identify your pieces. But this is the next step up where they're giving you it. You don't have to create it. And you just now have to find the points. So one extra step. So let's start by graphing y is greater than or equal to 2. So I'm going to go to my y value and go where y is 2. And y is 2 all along this. So we know that that is a nice horizontal line through y is 2. And if I want to be greater than or equal to that, it's going to be this area all above that. Okay. 1 is less than or equal to x, which is less than or equal to 5. So this is kind of tricky because it's a 2 and 1 jam-packed. This part you can see fairly easy. X is less than or equal to 5. And this part is just kind of flipped on us. So this is saying x is less than or equal to 5, but x also has to be greater than or equal to 1. So I want to go where x is 1 and where x is 2, 3, 4, 5. And I want to be between those. So I'm going to draw my vertical lines. Oops. And when you're doing this on paper, it might be a little bit easier than turning around. And this part of my function is between those two. So I'm going to kind of shade in between there. All right, last one says y is less than or equal to x plus 3. So this is slope-intercept form. So we're going to start at our y-intercept, or our beginning, so that means we're starting at 3. Our slope is 1, so that means I'm going to go up 1 and over 1 and kind of continue with the pattern until I feel like I can confidently do a nice straight line, so that should be probably more than enough. But we're going to connect it with a solid line. Hopefully you're going to connect through the points. And less than means we're going to shade below. So now we see where the 3 overlap. It's right in here. So that means that is our feasible region right there. So we can kind of identify our feasible region. Remember, the next step is to find the coordinates or the vertices. So I see 1 right here, and I can easily read that as 1, 2. So I have the point 1, 2. That's a vertice. I have 5, 2. Right here. I have 5, 1, 2, 3, 4, 5, 6, 7, 8. And then the last vertice is at 2, 1, 2, 3, 4. So remember, I have to use these coordinates to see which one is the maximum and minimum value to my objective function, which is right here. So I'm going to take 3x minus 2, that's my objective function, and substitute in my x and y's. So 3 times 1 minus 2 times 2 gives me 3 minus 4 is negative 1. Keep going. So we get 5, we want to actually have 3 times 5 minus 2 times 2. 15 minus 4 gives me 11. 3 times 5 minus 2 times 8 would be 15 minus 16. So I have negative 1. And then 3 times 2 minus 2 times 4 gives me 6 minus 8 gives me negative 2. All right, so that means our maximum came from the coordinates 5, 2, and actually gives me a value of 11. Right, this one was my biggest. My minimum came from the coordinates 2, 4, and that gave me a value of negative 2. All right, so I hope that helps. We will start to launch in to more word problems where we don't have any of this. All we have is the situation, but it gets fun and there's